Smartphone interfaces are increasingly accessible to users with visual impairments.
2:35 p.m. Facebook, Twitter, Hangouts, Skype.
On-body input is an alternative that provides tactile cues to help support accurate input, even without visual feedback.
Audible, Pandora, Music.
Despite these advantages, no previous work has designed or evaluated an on-body input system specifically for visually impaired users.
Skype, podcasts, Audible, Pandora, Music.
Our approach enables input at a variety of locations within the user's reach, and also supports new types of location-specific gestures. Our system, TouchCam, has several components worn on the finger and wrist. A pair of infrared reflectance sensors near the tip of the finger are used to detect touch events and for gesture recognition. A small camera at the top of the finger is used to recognize the location that the user is touching, and includes a separate LED to provide illumination as needed. Below the camera is an inertial motion unit, which is the primary sensor used for gesture recognition. And last is a wristband with a microcontroller to coordinate sensor readings, which connects to an external computer for processing and power. TouchCam's algorithms are split into 4 stages. First, the infrared readings are used to detect touch down and up events, based on when they cross a fixed threshold. These events are used to segment gestures and location input. Second, the system extracts features from the raw sensor readings. The camera has a close-up view of the touch location, and visual texture-based features are extracted from the video frames to use for localization. Meanwhile, the infrared and inertial values are processed to form a feature vector for gesture classification. The system smooths and resamples the raw values, and also extracts summary statistics, like the mean, variance, and correlations. The third and fourth stages run in parallel, using features from the previous stage to classify either location or gesture using support vector machines. Stage 3 uses classifiers that are trained individually for each user, first classifying coarse-grained locations like the palm or wrist, and then classifying fine-grained locations like the upper or lower palm. Stage 4 uses a single gesture classifier that is identical for all users, trained using a large set of pre-recorded gesture data. We implemented 3 interfaces applying these algorithms. The first interface allows the user to swipe left and right anywhere on their body to navigate a circular menu of applications.
Daily summary. Notifications.
A double tap gesture activates the currently selected item and opens its submenu.
Distance. You've traveled 1.8 miles today.
The second interface maps applications to specific locations on the palm.
Voice input. Daily summary.
The user can tap or slide their finger between locations to search for an item, and then double tap to activate it.
You have 1 missed phone call and 2 new messages.
The third interface is identical to the second, except that it attempts to map the applications to intuitive locations across the body.
Health and activities. Voice input.
For example, the clock application is mapped to the wrist, and the voice input application is mapped to the ear.
10:25 a.m.
Once an application has been activated, its menu can be navigated using swipes to the left or right.
Timer. Stopwatch. Alarm, set for 8 a.m.
We recruited 12 participants with visual impairments to use TouchCam while completing a series of simple tasks. We found trade-offs between the 3 interface designs in terms of sensing accuracy and user preferences. In general, participants liked the idea of on-body input and wanted to customize the locations and applications, something that our system could easily support. TouchCam is a novel multi-sensor approach to on-body input that enables flexible, location-specific gestures.